As space exploration has advanced over the years, the Earth has earned some pretty special nicknames, including the blue marble and the pale blue dot. This is because when you look down at our special oasis from orbit, one of our planet's most defining features are vast oceans. Because our oceans cover most of the planet's surface, it kind of makes sense that humans would really lean into them as one of our most abundant and valuable resources. But one could ask, how much do we really know about our oceans? My name is Cadence Payne, and I'm a fourth year PhD student in the Department of Aeronautics and Astronautics at MIT. My specialty is in technology and mission design for tiny bread loaf-sized spacecraft called CubeSats that are revolutionizing the way we conduct science on orbit. Having the bird's eye perspective of a satellite positioned above the Earth allows you to frequently monitor large regions of the Earth's surface, atmosphere, and other defining features like our oceans. When most folks think about satellites, they imagine these like bus-sized spacecraft that are massive, super expensive to make and launch, and require long development timelines because they're really complex. However, nanosatellites offer opportunities to monitor key characteristics of the Earth from space via platforms that are relatively fast to design and build, relatively cheap to manufacture and launch, all while supporting complex instruments, or what we call payloads, that are capable of collecting high-fidelity, large-scale scientific measurements. My research narrows in on the CubeSat world to focus specifically on the payload instrumentation, meaning the hardware that actually performs the science. So to constrain things even further, because working on broad topics for your PhD is really hard, I chose to focus on imaging payload positioned in these tiny spacecraft that target ocean measurements. So as I mentioned before, the oceans are vast, they're mighty, and while we don't know a ton about them, we do understand that they're deeply intertwined with our planet's climate and weather systems. So studying key features of the ocean, such as its color, surface temperature, and surface salinity, allows us to extract valuable data from the ocean's current conditions that serve as useful input to existing climate and weather models. Essentially, we're collecting fresh data about our oceans from space to help us understand and quantify the effects of climate change. Now, so far, I've been a bit vague about what I actually do here. So I'm working to develop a tool that simulates the sensitivity of an imaging payload on one of these CubeSats that looks at the ocean's color from low Earth orbit, or roughly 450 kilometers above the Earth's surface. We're targeting ocean color because it can tell us really neat things about phytoplankton concentrations, oceanfront locations, and even help us predict where large fish might gather, which can all be indicative of how the ocean is changing with the climate. My goal is to determine how large or small we can make the imager's aperture, or the lens collecting light from the planet, and to estimate the fidelity of the data we could receive from a spacecraft of this type. I'm conducting an investigation of different measurement band types and lens combinations we could use to look at ocean color to help determine which types of measurements will provide the best story about what's actually happening down there. This work will supply a tool to help folks in the future constrain their designs for ocean observing payloads on CubeSats, and will hopefully save them a lot of time determining which design best suits their science objectives. I hope that my work will help expedite the production of ocean observing CubeSats moving forward, so we can increase the number of eyes we have on orbit and continue the work towards understanding and mitigating the negative effects of our changing climate. Thank you.